Hello, my name is David Orrell, and we're going to be talking about a quantum finance approach to option pricing. So I'll do the first half, and Dominic Widows is going to do the second part on applications. So the basic idea is that mainstream neoclassical economics and quantitative finance got started in the late 19th century. At the same time, the first computers were being developed, and they picked up speed in the post-war era with the advent of high-speed computers. And now we have this view of finance, which has been shaped to a large extent by the sort of yes-no, zero-one logic of classical computers. And so today we're talking about quantum computing and how you can apply quantum computing in finance. And a related question is, now that we're thinking in terms of qubits and running stuff on quantum computers, how will that affect the way that we think about finance? The classical approach to finance is to assume that the system is at equilibrium, but perturbed by random shocks. So you can model the evolution of log price change x as a biased random walk. So you're discretizing in time when you run it on a computer. And the distribution after some time t will be a normal curve with a standard deviation, which reflects the annual volatility. And you might include a constant drift, typically equal to the risk-free rate. So the picture is something where at each time step, the price either goes up or down as you go along in time. So in the quantum approach, so I've talked about this in other presentations, and if you're interested in the details, you can check out the paper. But the basic idea is that you quantize entropic forces that act on probability. So the idea is that you're not assuming equilibrium, you're assuming that you have kind of restoring forces that are kind of corralling this probability into the center. And when you quantize that, you get an ensemble of quantum harmonic oscillators, which represent transactions over the complete period t. So you are not discretizing in time. And you have a superposition of imbalanced states, so no single drift, no equilibrium, no single drift. The property of a quantum oscillator is that it has a discrete energy number, n, and so we equate that with the number of transactions over the period for one individual oscillator. So this agrees with the classical model in the case n equals 0 with no transactions. So the quantum approach captures the dynamic and stochastic nature of financial transactions. And the trick really is that your time here is this is a picture of a complex valued wave function, which is rotating around the real axis. And it allows you to represent prices being in a superposition of states. So prices can be sort of both up and down at the same time, if you like. I'll just say this is the classical approach where the price is going up or down at each step. And the quantum approach, you have these restoring forces which are being quantized, and that allows you to have a complex valued wave function which is rotating around the real axis in time. So that's what that shows. Okay, so some properties of the oscillator. So the main one is that the relevant length scale is x over sigma, where x is log price change. But sigma scales with the square root of t in this model, so we use z equals x over square root of t. The imbalance between buyers and sellers, so remember that we're assuming that no equilibrium, so you're allowed to have imbalances, and this leads to price change, but also increases volatility. So this is true of large transactions. So for example, if you have a large purchase, it will increase the price, but it will also boost the volatility. For more generally, the volatility over a period t is related to the scale price change z over the same period by a simple equation. So you can check this for yourself. You just take something like index data is the best. You have like long historical data, and you can go back and just break it up into chunks of a few days or a few weeks or a few months. Calculate the volatility over each of those chunks and the price change over each, plot those, and you get something like this. I notice this is simple. The only parameter here is sigma 0, a sort of base level of volatility. And this bears a striking resemblance to the volatility smile in option pricing, which we'll come to. Another property is that the probability distribution is a Poisson-weighted sum of Gaussians as opposed to a Gaussian classical one. So it looks like this. So it's basically you have a number of terms which are increasingly larger standard deviation. So the n equals 0 term plus the n equals 1 plus the n equals 2 gives the red line. And the average value of n is given by lambda, which is about a quarter. So this model is kind of similar. If you're familiar with jump diffusion, it looks kind of similar in the sense that they're both Poisson-weighted sums of Gaussians. But in jump diffusion, if you have large T, this sort of saturates out, so sigma n just approaches sigma 0, which is not the case with quantum model. And there are other differences that they're really not the same. The core assumption of the classical approach is the no arbitrage principle. So you got the law of one price, which dictates that an asset has a single price across the market. And this is needed to derive the Black-Scholes formula, but it's also used in theories of implied volatility. In the quantum approach, we have the law of two prices, which says that there are at least two prices, the bid and the ask, and the difference between them represents a fundamental level of uncertainty, which is the main driver of volatility. So ignoring that bid-ask spread is like assuming volatility is 0. It's not very useful. In classical option pricing, you have the Black-Scholes model, which kind of assumes a Gaussian distribution. Drift is set equals to the risk-free rate because you can do this by assuming no arbitrage. So the only unknown parameter is the volatility sigma. However, opinions differ on its value, as shown by the volatility smile, which is often described as being kind of illogical or irrational. So this framework is simple and elegant, but really it exports all the complexity to finding sigma, so it's unfalsifiable. If you have a model where you can change the parameter to get the answer that you want, then it's not doing much. In the quantum model, you have this, again, this Poisson-weighted sum of Gaussians, so it's kind of sharper peaked and fatter tails. The no arbitrage condition does not apply because transaction costs depend on the bid-ask spread, which again is related to volatility. So for this model to make it work with Black-Scholes, you actually need the volatility smile. In the classical model, you could model the volatility smile using something like the stochastic volatility inspired model, which uses 5 parameters for each value of the expiration time t. And it gives this square root behavior in the wings, and this is by design because there's a theorem from no arbitrage which says that in the wings you should get that square root behavior. And again, this is just for one time t only. So this is a fairly complicated formula. You got these nested square roots and 5 parameters and so on. The quantum implied volatility is the volatility which gives the correct option price when used in the Black-Scholes model, assuming that quantum distribution. So you've got this parameter Q you can derive from theory that it should be about 0.95. And here the smile is linear in the wings with a slope about equal to 0.3. This holds for all times t. So to summarize, classical algorithms such as SPI treat the volatility smile as being sort of basically illogical or rational, adopt a curve fitting approach, which uses multiple parameters to fit observed data, but enforce no arbitrage. And the idea is to capture things like behavioral effects, which are assumed to cause the smile. The quantum model, in contrast, is a prescriptive formula in the sense that it says what volatility should be used as input to Black-Scholes, given the quantum distribution. It's derived from a model of asset price, so it does not attempt to account for things like behavioral effects or supply and demand. And the main parameter to fit is the minimum volatility. So how does this compare with observed data? Does it predict implied volatility, and can we use it to spot arbitrage opportunities? Well, here's an implied volatility service for the S&P 500 over about 17 years of data. So here, data is averaged at each X and T, where X is log price change, log moneyness. So the first step is to rescale to Z. So this is actually inconsistent with no arbitrage because those limits conditions, but let's do it anyway. So the options at the 1 year kind of, they stay the same, but the ones in the front kind of get opened out. And then the next step is to view along the t-axis. And so that's the view. And then you compare the quantum prediction. And this really is a prediction in the sense that the quantum model was derived from a model of asset price behavior, so nothing to do with options. So again, this is a prescriptive formula in the sense that it says what volatility should be used as input to Black-Scholes. So it does not attempt to account for things like behavioral effects, but it still captures the main features of the data. So it's like traders are kind of behaving as if they have a quantum model in their mind. And the model is not perfect, and you have these areas like here where there's kind of deviation between the model and the observed data. But that doesn't necessarily, mean that the model is, because it's a prescriptive formula, it doesn't mean that the problem is with the model. It can mean that these options are actually being mispriced in some way, and this is something that you can just go out and check. So that's a subject for another day, but you can just kind of compare option pay-ins and payouts for those options. Here's another view of some more recent data from April 2024 for options, SPXW options with expirations from 17 to 199 days. And this data was provided by Theta Data, and we're looking at ways to incorporate the quantum implied volatility models in their APIs. Same approach works for individual stocks. So this is for AIG. So again, you've got the 3D plot and the 2D view. This data was from 1 William Street. Okay, so from the quantum perspective, the quantum implied volatility is a numerical artifact which arises from using a non-normal distribution in a formula which assumes normality. Like Black-Scholes is based on normal, but if data isn't normal, then you have to correct it somehow. So the quantum model can therefore be used in two ways. The first is to run the Black-Scholes model using quantum implied volatility, like here. But really a simpler method is just to sort of bypass Black-Scholes altogether, forget about implied volatility, and calculate option prices directly from the expected payout under the quantum model, either classically or with a quantum device. And it's interesting. It turns out that you can approximate. So the idea is that you just need to get the quantum distribution correct. And it turns out that you can approximate that using a quantum walk with decoherence. So as Dominic's going to say, the quantum walk, it sort of has a tendency to have these two parts which are splitting apart. Decoherence it plays almost the role of that sort of decoherence, that restoring force that we have in the quantum oscillator, bringing the price back in, and you end up with a distribution, the red line, which is a pretty good match for the black line. Okay, so I'll hand over to Dominic now to explain how this can all be implemented on an actual quantum computer.
Thank you, David.